guest lecture of our course on deep and reinforcement learning. Today, we are very happy to have Ignasi Clavera with us, who will talk about reinforcement learning for real-world robotics. Ignasi Clavera is a research scientist at covariant.ai. He obtained his PhD from the University of California, Berkeley, advised by Peter Reville. During his doctorate, he worked in the intersection of machine learning and control, focusing on deep reinforcement learning and meta-learning. Specifically, he was interested in developing methods for efficient and generalizable real-world robotic learning. And at covariant.ai, he continues working on developing methods for real-world learning. Prior to his PhD, he studied mathematics and industrial engineering at our university, Universitat Politècnica de Catalunya, which was possible thanks to the CEFIS program. Ignasi, thank you very much for your time. Congratulations for your recent doctoral degree, by the way. And we are really looking forward to see how we can bring all these techniques that we have been learning in our course on reinforcement learning, because we always wonder like if there's an industrial application nowadays, and we hope that with your talk, we can get some insight on this. So, it is yours. Thank you very much, Ignasi.
Thank you. Okay, let me first, okay. Cool.
We can see it now. We see, yeah, we see your screen perfectly well. Yeah, perfect. So, thank you. Screen is yours. Thank you.
Yeah, well, I'm going to talk about reinforcement learning for real-world robotics. And this is work that I did during my PhD at Berkeley. So before we delve a little bit into the topic of reinforcement learning and how to use it for production and like for real-world applications, I want to talk a little bit about like the current state of robotics in the real world nowadays. So here we can see some images like from this Tesla factory and a warehouse in Amazon. And so nowadays robotics are very much used for industrial applications. However, the current applications like are in very controlled domains. Like here in the factory, we have very precise movements. Everything is always at the same place, and there's like very little variability. And this is the same for the case of like the warehouse. So as a result, like you don't need like any learning or like any fancy artificial intelligence here, because all the movements are just like handcrafted because everything is very controlled, as I said. However, this is not like what we would like to have from these robots. We would like to them like to interact with them in the real world, like help us in our daily lives. For instance, you can see a video here that Willow Garage presented when they released the Pier 1 robot. This is a video from 2008. This is 12 years ago. In this video, we see the Pier 1 robot doing like chores or chores of the house that we would like them to do. And here, like the robot, it's teleoperated, so it's not autonomous. There's someone just controlling all the movements. And we see like it even fetches a beer for us when we were watching TV. So this is kind of interesting because this video was released 12 years ago, and they were thinking like we will have this soon, but like we are not there yet. Like there has been a lot of progress, but we don't have the capabilities right now to have this degree of autonomy and general ability. So before we enter on the topic of like deep reinforcement learning and how to apply it to real-world robotics and how to scale it, I want to show you like what are the current approaches and that people have used and why they're not sufficient to achieve all the capabilities that we see in this video. So here I'll present like there's like a plethora of methods, but I will present the three that are mostly used. And these is like first trajectory optimization, then handcrafted controllers, and finally imitation learning. So in trajectory optimization, how it works is like you have a description of the world, and then you run some planning algorithm or some like optimal control algorithm to find the solution or the movements and the positions that you will need to do in order to carry out a task. The main limitation with this is that you need a detailed description of the world. And as a result, this makes it very, very hard to scale. For instance, you can see you built a robot, and you make it work in this specific kitchen. So like you know everything, how all the dishes and all the drawers were positioned, all the caps and everything. However, your robot will not just work in this kitchen. If you want it to work in like another kitchen, for instance, this one that is messy, you will need again to create like an entire simulation of this kitchen. And this is like a very expensive process. And as a result, like it makes it impossible to scale to like digital ability, but it might work very well on like factory settings that we have seen before. Another complication with this method, this sort of methods, trajectory optimization methods, is that it's hard. There are things that are hard to model. For instance, like fluid or cloths. Imagine just predicting every wrinkle of this scarf. So there are like some objects here that are like just like impossible, almost impossible to model, and therefore we cannot create like a dynamics model of these items. Then we have the other methods is handcrafted controllers. And handcrafted controllers, how it works is like at every specific state, you say what you will have to do. Here we have an example from a paper in 2010 that is like towel folding. And here at each step, it will say like, oh, pick up a corner, or pick up this, and it will just like continue the process. The thing with these sort of methods is that there are tasks that the optimal controller is very hard to describe, or there are tasks that like we don't even know what's the optimal controller. As you can see, like self-driving cars, like what you should do in each situation, it's not very easy to describe. The last set of methods is imitation learning. Imitation learning, how it works, it's at every point in the state, you tell the robot exactly what's the action you should do. And this can be done by like here, like teleoperation, or just like moving yourself the arm. The issue with this method again is that it's hard to scale and it's expensive, because like the reason for this is like you need a lot of supervision. For instance, here in a recent paper from like Justin Fu, he did imitation learning in a set of different tasks, but he will need to provide like 100 trajectories for each of the specific tasks. And these tasks, they are not like that different. So that makes like, if you want to do more complicated tasks, you will need even more supervision. So also like this high degree of supervision makes imitation learning sort of like expensive to scale. So we see that these three methods, trajectory optimization, handcrafted controllers, and imitation learning, all of them have limitations to accomplish this goal of like the video that I show you, to have robots kind of like helping in our daily lives. But I'm here to talk about like another method that it's reinforcement learning. And from my point of view, reinforcement learning kind of like is able to overcome these limitations that these three methods presented. And I see it as like the possibility to allow us to have like this degree of autonomy for robots. I guess most of you know how reinforcement learning works, which is like a brief summary. So in reinforcement learning, you have an agent. In this case, we're interested in robots, but it could be any other thing. And at each time step, it takes an action. And this action results in a change in the environment. As a result of that action, as a change in the environment, the robot or the agent receives a reward. And the goal of this agent is to maximize the sum of rewards across this trajectory. As a result, reinforcement learning presents like several advantages from the previous methods. So first of all, you need a model of the environment. You learn purely from interaction. As a result, like you don't have these limitations that trajectory optimization presented. Like you don't need to describe every single scenario and know exactly where everything is. Another thing is like you obtain the optimal policy with respect to the reward. And just like overcome the limitation that handcrafted controls presented, like that it's hard to describe the optimal controller, or like you don't even know. Here, in reinforcement learning, through repeated interaction, it will arrive to the optimal policy. Lastly, you need minimal supervision. The only supervision that you need is this single scalar that is the reward. So you don't need like this dense supervision needed in imitation learning, where you need to say exactly like at each stance which is the right action that you should do. So it's all like reinforcement learning have had a lot of successes, and probably most of you know all of these. First, like the Atari, the DQN paper, where like they play like human or superhuman performance at Atari video games. Then there was like this paper from John Schulman, Choice Region Policy Optimization. They show for the first time that like deep reinforcement learning was able to learn these complex locomotion policies. And then lastly, we have like AlphaGo or AlphaZero that be like that be the best human at playing Go. However, like these same successes sort of like points also the limitations of reinforcement learning, because all of these successes are in domains where data is cheap. You can see how much it will take to learn these games in the real world. It would be like 40 days for the Atari. Well, humans like tend to play these games like pretty well, or pretty decent after like just a couple of hours. It was like 10 days to learn these like locomotion policies, or 8 years to continuous playing of Go. Obviously, like these algorithms didn't take that long, since like they exploit like deparallelization, and that they are able to render data faster through GPUs and computing. But this is what it will take for a human to just learn these things. However, the issue with robotics or real-world applications is that data is typically expensive. So, for instance, like in robotics, in the case of robotics, you can have wear and tear. That means like if you need to learn for like 40 days straight, like the robot will most likely break or something will happen. It will also like create like hazardous situations, and those are situations that, since like the robot doesn't know what to do at the beginning, and this learning of reinforcement learning happens by trial and error, it can result like in unsafe situation. I mean, like it could be like stupid, like just dropping a plate, but it could also be like more serious situations like hitting someone that's around. Finally, it just like takes a long time if you need to train for 40 days, because in this case, parallelization is expensive. What it means parallelization in the real time, in the real world, it means to have different robots. And even like the price of robots have, in the recent years, kind of decayed. This is still like a robotic arm costs like around $40,000. So it's pretty expensive to parallelize this process. As a result of these three components, collecting data in the real world is expensive, which sort of makes these reinforcement learning algorithms a little bit hard to deploy in the real world. So what I presented here, it's reinforcement learning, but like it's specifically how what it's called model-free reinforcement learning works. However, there's another set of methods that are called model-based reinforcement learning. And this set of methods operate in the same paradigm than model-free reinforcement learning methods, and that's the methods I just described. But they have like a few more steps. So what you have by this repeated interaction with the environment is that the agent collects this data, and you store this data into a replay buffer. Then what you do with this data is to learn a model of the environment. And this model can be your favorite function and prediction feature, linear model, neural network, whatever you want. But you learn this model through like standard supervised learning by predicting from the current state and action what's the next state that the robot observed. Then you use this learned model to train the policy on top of this. So you train the policy on top of the learned model instead of the real world environment. And the goal is the same. The goal is to maximize the sum of rewards across an episode. So here we can see, like in a pseudo algorithm, you have these three steps I just presented. one, collect data under the current policy, learn the dynamics model from the previous data you've seen, and then improve the policy by using this dynamics model. And you keep repeating these 3 steps until convergence. So the main benefits of model-based reinforcement learning is that it's more sample efficient. The reason for that is like it exploits much more the data you have obtained, because you learn first the dynamics model that is like very efficient, because as I said, you do it through supervised learning. And then you carry out the data intensive part, that is learning a policy, on top of the learn model. So as a result, the samples from the learn model are essentially free, because you don't need more interaction with the environment. You just learn on top of this, learn the policy on top of this learn model, and then you end up obtaining the optimal policy. Another benefit of this is like once you have learned a model for a specific dynamical system, then you can reuse this model to learn different tasks. And this is by tasks, meaning different reward functions. And now the one other question is like why we haven't seen these successes with model-based reinforcement learning. Why did you just present successes on model-free, these like Atari, Locomotion, and Game Board? The thing is like most of the algorithms that we previously and still like a little bit currently have of model-based reinforcement learning are limited to simple domains. And they typically also have a performance that it's below the model-free method. So they don't attain the same level of optimality as model-free methods. So before we delve into like the main problems of model-based reinforcement learning and how to tackle them, just want to previous recap of like the story we've seen so far. So we want real-world learning. Previous approaches are not suitable because they are expensive to scale, they don't achieve optimality, or they just need too much supervision. Then we see that reinforcement learning is an exciting alternative to these methods. However, reinforcement learning, it's too sample inefficient. It needs too much data, which in the real world is expensive. And here we have presented like this framework of model-based reinforcement learning that kind of like has the promise to be able to overcome the data inefficiency of reinforcement learning. So okay, let's see like the issues of model-based reinforcement learning. So the main issue is what is called model bias in reinforcement learning, and this is like a very like kind of like abused term described to like that essentially people use it to describe all the issues with model-based reinforcement learning. But I would like to decompose it into 3 main problems. One is approximation errors. The second is compounding errors. And the last one is over-optimism. So let's look at each of these one by one. So first, approximation errors. So this approximation error is kind of like inherent of all learning methods. The thing is like you're learning a policy or an approximation of the real world environment, right? So like the learn model will never be exactly the same in the real world environment. As a result, like a policy that is optimal in this learn environment might not like fully succeed on the real world. And this like happens always, like every time you learn something or you approximate something, you will have like this gap between your approximation and the ground truth data. The second issue is compounding errors. And these compounding errors happen because of the sequential nature of the reinforcement learning problem. The thing is like this, even in supervised learning, because this is an issue of supervised learning actually, is that your model is just good in the regions or in the distribution that you train it on. So it will just be good on the regions like it has in data. So for instance, let's consider we just gather a bunch of trajectories. Each of these dashed gray lines corresponds to a different trajectory. and we train our model on top of those. Then, because we have this approximation error, even if your model is like very, very good, the predicted state, that is the red line, and the true state, that is the blue line, will differ a little bit. And because the way that these models are used, it's by what is called open loop prediction. That is that you predict the next step by feeding the previously predicted step. This error will just like keep growing and growing and growing. And there will be, at some point, your model will start visiting states that it hasn't seen any data on. As a result, like from that point onward, typically the prediction of the model are just garbage because it just like hasn't seen those states, so it doesn't know what's the right prediction. Then your policy will be learned on top of the states that are garbage, essentially, and it will not learn how to succeed in the real world. The last problem is like actually the most interesting one, and it's what it's called over-optimism. And this is like the previous two were like kind of like inherent of supervised learning too. And this is like very much like a thing of just reinforcement learning, or when you learn models and train policies on top of learned models. So how this works is it's in the first step that you collect data, you will learn the model. And as a result, this model will just be good on regions that it has seen data, as I explained before. And as a result, like there will be regions of the state that like it will not know what's the right thing to do. Then when we train a policy on top of this learned model, and here the policy, it's finding the correct path and the shortest path from the initial state to this goal that is the start. What it will do is learn the shortest policy on top of this learned model. As a result, it will find a path that is the shortest path in this learned model. But however, this path, when you deploy it in the real world, what happens is like it goes through a wall. So like the robot will just like catastrophically fail. So we see that like the policy, because it's learned on top of this approximate model, it will exploit all the shortcuts of the model. That these shortcuts might not exist in the real world, as we see here. And then when you deploy the policy on the real world, it just fails. So I will first present a method that it aims to tackle this model bias and this over-optimism, sorry. And the solution is it's kind of like pretty straightforward and it's kind of nice. So what you do is you first have the same step of collecting data, but what you do now is instead of having just one model, you learn a bunch of different models. So you will learn one model that will have this shortcut over here, but then you will learn a different one, and this different one will be as good as in the regions that it has seen data, but then it will present like a different maze configuration in the other part of the state. Then you will learn just a bunch of those, and what you will do now that you have your models, it's instead of learning a policy that it's good on like the best model that you have trained, that will probably mean the model that has like the smallest validation error. We'll do is like learn an optimal policy on all of these models. So there is like a policy that is good on each one of them. As a result, like this shortcut that the policy will learn here, it will not work since this shortcut will not succeed in this other model. So as a result, it needs to learn a policy that it's consistent across all the models. And this consistency across all the models, what typically results is like also consistency with the real world. And this lets us with a policy that presents like that has success in the real environment. So we can easily modify how this canonical model-based reinforcement learning algorithm works, and using this idea of learning a different models to present like a new algorithm. This is an algorithm that we presented at iClear 2018. And the way that we tweak canonical model base is by, you have the first step of collecting data on the current policy. But then what you do is you learn an ensemble of dynamics models using this past data. And this ensemble in our case was just like 5 or 10 different neural networks that each of those were trained with like a subset of the data. And each of those has like different initialization of the weights of the neural network. And this was enough to just have enough diversity in the models. So we'll use this policy, we'll learn this policy by using model-free. So specifically, we use the characterization policy optimization algorithm. And we use these model-free methods on top of the ensemble, so it's like optimal across all of those. So what seems like this like MATRPO algorithm, the one that we just described, we tested in like, in these like 5, 6 different environments. And our algorithm is the green curve, and the blue is like a similar version of our algorithm. And we see that like as we go to more complex domains, first like we have a very simple domain, it's called the snake. Then we have the help cheetah and the ant rabbit, that's like the most complex one. We see that the gap between the performance of like this method that we just presented on the canonical model base, is the red one, increases, our method like giving like superior performance. So you can see that you can tackle this like over-optimism and this model bias problem by using an ensemble of models. And this results in an algorithm that like gives you much better performance than what prior model-based reinforcement learning algorithms had. So we also compare against model-free, and these like models, algorithms that don't learn a dynamic model, so they just learn through repeated interaction with the environment. And we see that like our method in these simple domains can achieve like 100 times more data efficiency. Notice like the scale in the x-axis is log scale. However, like one limitation of this algorithm is that as you go to more complex environments, that is like this ant and this humanoid agent, the issue that we have is like our method is not able to achieve the asymptotic performance, like the optimal performance, and this is like dashed with this like black dash line. So by tackling like this over-optimism with ensemble of models, you can get like a very, very efficient model-based algorithm that has the same performance than model-free methods. That means like almost optimal performance in simple environments. But you still have a gap in the more complex ones. The issue with this is that you have this underlying assumption that the real world dynamics, it's some combination, or it's in distribution with each of the models of the ensemble, which this is definitely not true, especially in complex environments. And then learning a robust policy on all these models is not the optimal one for the real world. Like learning a policy that is good across a bunch of environments, it's a much more harder task than just learning a single policy in the real world one. So this method that I presented is just kind of like tries to tackle these like over-optimism, but it doesn't tackle the issue of like approximation errors and compounding errors. And the thing with this is like any learned model will present those. So like it's not like something that you sort of kind of escape. So what we thought is how can we achieve model-based algorithms that kind of like lead to the optimal performance. However, taking into account that like any learned model will present these first two errors. So what we did instead, like learning an optimal policy and a policy that is good across like all these models. It's to learn a policy that can, or that it's good at adapting to different dynamics. So what that means is like from a little interaction on each of these dynamics models, you will learn a policy that it's optimal on that one specifically. And you will train one of these with several dynamic models. And the way that we will do this is through meta-reinforcement learning. And I think like Farhan like talk a little bit on meta-reinforcement learning. So I'll just give like 5 cents on this. That it's in reinforcement learning, you have Nijin, a real world and a task. And in meta-reinforcement learning, what you have instead is like a different task. So, and each of these tasks is represented by a different reward function. So you have the same dynamics, but different reward functions. And your goal is to learn a policy that can adapt quickly to a new task. So you don't want a policy that's good in a specific task or that is good like in a bunch of tasks. You want a policy that through like very little interaction, it can adapt itself and be optimal in that specific task. So this is like the idea we came up with in model-based reinforcement learning via meta-policy optimization. And what we did is instead of considering tasks different reward functions, you will consider a task different dynamics model. So the main idea is that through meta-reinforcement learning is that you get a policy that with like minimal interaction, it knows in which dynamical model it's in, and then it adapts itself and in order to become optimal to carry out the task. Then we train it in different learned models, and then test time, which is adapt to the real world dynamics. As a result of like this adaptation in the real world dynamics, it kind of like it's able to overcome the approximation errors that we were describing before. So we can very easily tweak the previous algorithm that we presented before, this like model ensemble characterization policy optimization, to describe like the new algorithm that uses meta learning. So you'll perhaps the first step of collecting data on the recurrent policy and learning an ensemble of dynamics model from all the past data. But then you will improve now the policy by using meta learning. And then you will use meta-reinforcement learning to learn the policy. The key thing is like to consider each model as a different task that you want to perform on. So here you first can see a video of this Walker agent across like different like minutes of experience. And on the left side, you have this like MBMP algorithm that we presented. And on the right-hand side, you have VPO. It's a model-free algorithm. And you can see that like with like 45 minutes of real-world experience, our algorithm is able to start running forward and moving, while a model-free algorithm is still in the exploratory phase of like figuring out how to move its limbs and what to do. So here our algorithm is the red curve. Again, the x-axis is log scale. And the other different methods are model-free algorithms. And we see that like across all environments, our method that uses meta learning to learn a policy across different models is able to accomplish like the optimal performance, again, like this dashed line at the top, and is able to do it by like also being like between 10 times and 100 times more sample efficient than model-free. And here we also compare it against Modelbased, and red line being the meta learning method, and the blue line is the previous method that I just presented. And we see again that, like, in more complex environments like Ant and Walker, our method surpasses the previous model-based methods. So the takeaways is that you can exploit these approximation errors by having more diverse tasks. And this is by having like more diverse and different learn models, and then use meta learning on top of those to learn adaptable policy. And doing this, you can have an algorithm that achieves the same asymptotic performance as model-free, but also being 100 times more sample efficient. So this is where we have tackled these approximation errors and compounding errors. And in the previous work that I presented you, we tackled the over-optimism. So it's all to obtain like a set of methods that are effective at overcoming the limitations that model-based have. And we kind of tested this on the real robot. And here the task is to stack the red block on top of the yellow one. And left-hand side, it's the MBMP algorithm, this model-based method I just presented. And on the right-hand side, it's the model-free algorithm. It's called PPO, or proximal policy optimization. And we see that like our method in 10 minutes, it's able to just like solve this task of like stacking one block on top of the other, while like the PPO algorithm and these model-free methods are still again like this exploratory phase and figure out what to do. And it will just like take hours for them to finally solve the task. So I hope that you like this talk, and because like this offers like a promising venue of like set of methods that will be able to enhance the capabilities of reinforcement learning and allow us to have like this degree of like generality of robotics and be able to like make them more have like a widespread adoption of them. Thank you.
Good. Thank you very much, Ignasi, for this very interesting talk. So as usual, now we'll just move to the classroom with our students, together with Ignasi. And for those of you who are watching this online, just notice that next week we don't have any lecture, but in 2 weeks we'll have 2 hours of lectures by Uriol Viñals. So hope to see you there online. Okay, great. So Ignasi, you can just turn your camera off, and then we'll move to the other room. Great.